All right, pencils down. Pass your papers to the front. Okay. Yeah? Are you confident in this argument? All right. So the burning question right now is, what was so special about Theorem 17 from last episode? Okay, so what that there's associativity, identities, and inverses? Who cares? What does that do for us? To answer this question, we need to go on a bit of an
Algebra detour.
So set aside all your topological knowledge. We'll come back to it eventually, I promise. We're starting fresh with algebra right now. And let me nip this right in the bud. When we say algebra, we're not talking high school algebra, solve for x algebra, quadratic formula algebra. Although there is a genealogy back to those topics. Algebra to us is often called modern algebra, or abstract algebra in your course catalogs. It's a whole field of mathematics, so like topology, it's kind of hard to give a quick and succinct sales pitch. A very crappy definition is that it's the study of structure, but that doesn't tell you anything if you aren't already in the know, and could apply to a lot of math that I wouldn't call algebra. At first, our algebra will involve groups, and then eventually more stuff like rings and modules and categories. Maybe for now, to define algebra, we'll pull a Justice Stewart. I know it when I see it. That's a big boy joke. Okay, so algebra's a big topic. Great, thanks for sharing. Today, we only care about one small slice of it. By the end of the day, we want to have defined a group. And we could certainly do that right now and call it a day. The definition is a bit long, but I could tell you all the words, and then we could wipe our hands and say see you next time, and then see each other next time. But I want us to really feel the definition of a group in our bones, so let's take our time. Okay, consider the integers z, just all the positive and negative whole numbers and 0. Most of us would probably agree that these are nice numbers to deal with, but what exactly makes them nice? There are several good answers. Perhaps most people jump to, they aren't fractions. But let's focus on something even more fundamental. You can add them. If I give you two integers, a and b, then you can compute a plus b. And this is crucial to point out, it'll still be an integer. I can also undo adding. That is to say, we can subtract. You could just as easily compute a minus b, which will still be an integer. Actually, note that this isn't a trivial thing to have happen. You already know some sets where you can't always subtract. One is the natural numbers, n, which are just 1, 2, 3, so on. For the sake of example, if a is 2 and b is 7, then a minus b, 2 minus 7, is not a natural number. If we want to be able to add and subtract, we can work just fine in z, or q the rationals, or r the reals, or c the complex numbers. Whether we add or subtract in those sets, we won't ever leave the set, like we did in n. But what about a more esoteric example? Consider a 12-hour analog clock. You can add times. Starting at 4 and adding 3 hours, you end up at 7, so 4 plus 3 is 7. More interestingly, say we wanted to add 2 hours to 11. In z, that's 13, but there's no 13 on our clock. So we roll over and we say that 11 plus 2 is 1. Subtraction works in the exact same manner. If we start at 2 and go back 5 hours, we end up at 9. If your gears are turning, you might realize that there's nothing stopping us from considering some hypothetical fantasy world where they have 10-hour clocks, or 17, or 328, or 24, heaven forbid. At any example, we can still add and subtract as long as we roll over at midnight, whatever midnight may be. What about something even more different? We could stretch this idea of adding subtracting even further. What if we wipe away all the baggage that comes with the words addition and subtraction? Really, all we're really asking to be able to do is do and undo some operation. Perhaps an example in this manner would be a Rubik's Cube. Twisting a side is an addition, and untwisting it back is a subtraction. It turns out that wanting to add and subtract is a pretty rudimentary ask of a set. In some sense, it's just about the bare minimum that you would want to be able to do. As we'll see, the definition of a group is essentially built so that groups satisfy the bare minimum of being able to add and subtract. Our goal is to make a definition that captures the basic behavior we saw in these previous examples, but in a more general fashion. So the first thing we're going to do is give a good definition of addition, only we're going to stop calling it addition. We don't add Rubik's Cubes. Instead, we're going to call it a binary operation. Here's the definition, and then we'll talk through it. If we have a set S, then a binary operation on that set is just a function, I'm going to write dot, from S cross S to S. Keep in mind though that for weeks now we've been talking about functions pretty much only exclusively in terms of continuous functions on topological spaces. But that's not what's going on here, so it might take a minute to shake off that idea. Remember that a function, all it is just a relation such that every input has a unique output. So this dot function from S cross S to S is just taking two elements from S and outputting an element from S. In our usual function notation, we would write plugging in two elements A and B into a binary operation, like dot of A comma B. But to highlight the fact that you should think of this like addition, or actually multiplication, we're going to write the binary operation like A dot B instead. Sometimes if the binary operation is obvious in context, like if we're only talking about one particular binary operation at a time, then we won't even write the dot. We'll just smash the two inputs together. This is called concatenation, and it just looks like AB. Most arithmetic you've done in the past are examples of binary operations. Addition, subtraction, multiplication, and division of real numbers are all binary operations. You start with two input real numbers, then you add, subtract, multiply, or divide them, and you get a third real number. So this definition isn't telling you anything like remarkably new. It's really just putting a concept that you already had on more solid footing, so that we can be exact when we reason about it, or when we generalize to things that aren't addition, subtraction, multiplication, or division. With that definition established, we can now define a group. A group is a pairing of a set G with a binary operation dot from G cross G to G, such that 1. The operation dot is associative, in other words, G1 dot G2, then dot G3, is the same as G2 dot G3, then followed by, dot G1. There is an identity element E in G, such that for all G, E times G is the same as G times E, which is just G. And 3, every element has an inverse element. For all G, there exists some H, such that G times H is the same as H times G, which is the identity E. Okay, let's unpack. So a group is a set G plus the binary operation. Kind of like how a topological space is a set X plus the open sets tau. Then we throw in some requirements on that binary operation, but those requirements are things that you've already had experience with. The first is that it's associative. What this means is that it doesn't matter how I choose to group things if I'm computing multiple binary operations in a row. Whether I choose to compute 1 plus 2 plus 3 as 1 plus parentheses 2 plus 3, which is 1 plus 5, 6, or as parentheses 1 plus 2 plus 3, which is 3 plus 3, again, 6. I get 6 either way. To use leading language, whether I choose to associate 2 plus 3 or 1 plus 2, I get 6 either way. In fact, this associative property is really just saying that there's no need to use all these parentheses. We can just write 1 plus 2 plus 3 without having to impose in what order we're going to add those up, because in either order we choose, we're still going to get 6. The second requirement on my binary operation is that I have some identity element in my group. If we're speaking in generality, we often use the letter E to denote the identity element. The identity element is quite special, because it says that when I run my binary operation on the identity and another element, I just get back that other element. If we keep thinking in terms of addition in the integers, the identity is 0. We certainly know that it's the case that if you give me any number A, then 0 plus A is just A, and A plus 0 is A. So 0 is the identity element. The last requirement says that every element needs an inverse. That just means that if you hand me any element, I can cook up another one, such that when I run the binary operation on the two of them in either order, I get E. For instance, the inverse of 3 in Z is just negative 3, because 3 plus negative 3 and negative 3 plus 3 are both 0. We typically write the inverse of a generic element G as G superscript minus 1. Or, if we're dealing with a group where we write the binary operation as addition, then we'll write minus G, negative G. It's exactly what you'd expect. So, by unpacking the definition of a group, we've actually demonstrated that Z, with the addition we all know and love, is a group. It's worthwhile now to check that all of the off-the-cuff examples we gave at the beginning, like adding clock hours or twisting sides of a Rubik's Cube, also form groups. The clock examples are modular arithmetic. The binary operation is called addition mod n, and the group itself is called z mod nz, which has sophisticated mathematical meaning that we don't really know yet. The Rubik's Cube example is called the Rubik's Cube group. Now that we've got a definition, let's do our due diligence and see some examples and non-examples. So certainly z is an example, as we've just seen. To see that z mod nz is a group, let's take z mod 12z as a specific example to keep us thinking in terms of clocks. The elements of this set are the numbers mod 12, so that's 0 through 11. If you were thinking in terms of a clock, we're relabeling 12 as 0, because we're going to see that it plays the role of our identity element, and it'll gel with our monkey brains a little bit better to say that 0 plus anything is that thing than it will to say 12 plus anything is that thing. Now, the binary operation is that we add two numbers together, but if the sum happens to leave our set, then we subtract 12 until we get back into the set. Modular arithmetic is a smidge more sophisticated than that. We can define everything in terms of division algorithms and remainders and equivalence classes mod 12, but this notion of subtract 12 over and over until you're in the range from 0 to 11 gets the job done for us. And maybe later we'll revisit this if we do some number theory. Now, by construction, our binary operation is well defined. We take two numbers from 0 to 11 and get a new number from 0 to 11 because we forced the sum to land in that range. The operation is associative for the same reason that it is for z. Add three numbers in whatever order you want in z, then subtract 12 until it lands in the right range. The identity is 0, of course, since 0 plus anything from 0 to 11 is that same number. Inverses, though, are a little fiddly. In z, we can say that the inverse of 3 is negative 3, but that doesn't work here because we don't have a negative 3. Our numbers are only 0 through 11. But notice that every multiple of 12 in z is equivalent to 0. We can just see that by subtracting 12 over and over until you hit 0. So that means, for instance, that 12 in z also plays the role of 0 in z mod 12z. This is why it was okay to relabel our 12 on the clock as 0. So we can see that an inverse is just going to be a number that we need to add to reach 12. So the inverse of 3 in z mod 12z is 9, because 3 plus 9 is 12, which is 0. Another way to find an inverse is to first find the inverse in z, then do our move by 12 until we get into the range of 0 to 11 process. So in z, the inverse of 3 is negative 3. If we need to be in the range 0 to 11, we can add 12 once to get 9. So the inverse of 3 is 9 mod 12. Great! Just as valuable as playing with an example or two is to see some non-examples. Some things that look like they could be groups, but aren't. Your homework this week is to tell me why the following are not groups. And heads up, to keep you on your toes, I'm mixing in some things that are groups too. It's your job to tell the difference. So, 1. The set of negative numbers with binary operation multiplication. 2. The integers with subtraction. 3. The even integers with addition. 4. The odd integers with addition. 5. The reals with multiplication. 6. The reals minus 0 with multiplication. 7. The reals minus 0 with addition. And for bonus points, come up with the most esoteric example of a group that you can. The more unique and out there, the better. I'll see you next time.